Okay guys, in this video we're going to kind of recap some of the processes or techniques we use when solving trig equations, but essentially we just want to boil it down to one effort here, and that is to isolate our trig functions when we do this, because really in any of these equations you see here, what we're trying to solve for is this unknown angle. So in this case, like maybe x, or in this case 2x. Regardless, we're going to want to isolate the trig function in every possible instance. So that's what we're going to focus on here, is just this idea of how we solve these by isolating and what you do when you can't isolate the trig function. So let's go ahead and take a look at a real quick set of steps. I boil this down into, I guess, two types of equations, and I would classify these either I can easily isolate the trig function or I just cannot easily isolate the trig function. So with respect to this first type, this would be something where I could get the trig function by itself really easily. Essentially, we're going to go ahead and do so on the first step here, but then we're going to use an inverse trig function to undo the trig function we were given in order to solve for the angle. And then using our knowledge of the unit circle, we're going to go ahead and solve for what those angles are specifically. And so let's go ahead and assume that I'm going to solve for all angles here on the interval from 0 to 360, and I'll use degrees. But looking at example number 1 here, I noticed that it would be really easy to get sine by itself by subtracting 1 from both sides and then dividing by 2. So I get 2 sine x equals negative 1. Dividing by 2 here, I suppose we would get the sine of x equals negative a half. Now with respect to our steps, this was just step 1, but that was the whole effort, was to be able to get this by itself, because on the very next step then what I can say is if I take the sine inverse of both sides, then I know that my angle, or just my angle, would have to be the sine inverse of this negative 1/2 ratio. So step 1 is completed. Now we've completed step 2. Now step 3 is going to be this idea that, if I know whether or not sine is positive or negative, in this case it's negative, I could narrow it down to which quadrants this must have terminated in, and I know that sine is negative in these two quadrants down here, 3 and 4. So with respect to our angles, we're going to consider what next our reference angles should be here, and if sine's equal to a half, I'm going to go ahead and trace out at least our 30, 45, and 60 here. But with respect to all of these points here, remember that these give the value of cosine and sine, and that also all of these values at the very least are over 2. So I'm going to cheat a little bit here, and I won't cheat. We'll just fill them in. We say 1 over 2, root 2 over 2, root 3 over 2. We're going to need these anyway. So they go back up, 1 over 2, root 2 over 2, root 3 over 2, and we can find our tangent values from these if we need them. So with respect to these, I could say, well, where's sine a half? Well, where are my y values a half? They're a half at 30. So at least I know that this is a 30-degree angle that it makes with the x-axis. So with respect to what the angles actually are, of course, we're looking for these angles in standard position. We must be 30 degrees past 180. So in other words, we get one solution at 210. Sorry, 180 was on my mind there. And then the other solution would be at 30 degrees shy of 360, which is 330. Now, for the remainder of these problems, what I'm going to tell you is that I'm going to go through the processes of getting this trig function by itself, and then rely upon you to be able to do an inverse trig function and then work backwards towards the angles. So this last step right here, I'm going to kind of leave up to you. The whole idea of this video is, can you isolate the trig function and undo it with an inverse trig function? So we're going to go ahead and take a look at example 2 then. Example 2, I notice, is very similar to example number 1. As a matter of fact, the only thing that I changed on it was the fact that I have 2x inside my angle. So, and I made this a negative. So we're going to switch some things around here. We're going to add the 1 and divide by 2. Our goal, remember, is to isolate the trig function, except for this time we just have sine of 2x equals a positive a half. So isolating this trig function, the next step is to use the appropriate inverse trig function to undo this. We would use an inverse sine to undo this, and what we get left with on the left side would just be the angle, which in this case is 2x. And so we get 2x equals the sine inverse of a half here. So with respect to this, actually I will go through finishing this one here. We would say, first of all, what quadrants would I have to be in if sine is positive? And we know that you would have to be in the first, but also if it's sine, we could be in the second. All students take calculus as our mnemonic for remembering this here. And so our reference angles here, remember sine is a half at 30 degrees. And so if I know this is 30, and I know this is 30 with the x-axis, then we know this. And this is two things we know. We know 2x is equal to 30 degrees, but we also know that 2x is equal to 150 degrees. So the other step that we have to take here is we have to make sure that we finish up by just dividing these by the coefficient of x, which in this case leaves us with either x is 15 degrees or it's half of 150, which is 75. Okay, so that just has one additional step that we have to take in order to solve it. Now example 3, a lot of people get confused on 3. It's because you have cosines on both sides. I just would tell you, you would treat this just like you would any expression that looks like this if you were solving for x. The very first thing we do is get all of our x's on one side. Specifically, if I had this equation, I would add 4x to both sides, because what that does is it essentially clears all my x's off of one side. And what I get left with is x's being all on one side. Now I can start moving things away from it. So in the same light, I'm going to add 4 cosines to both sides here. I mean, they're both already like terms, so why not get them off of one side? And what we get left here is 2 plus 2 cosine, not sine, cosine of theta equals 3. So from here we could do some other things, like I suppose we could subtract our 2 over to the right-hand side. If we subtract 2 from the right-hand side, we're further isolating our cosine value here, but we get 1 on the right, and then dividing by 2 on both sides here, we get a fairly common value for cosine. So from here, cosine inverse, but we had to isolate the trig function. That was our goal. We did it. We used an inverse trig function. Now, for the remaining functions that we look at here, we're going to look at functions that are not easily isolated. But basically, if they're not easily isolated, then what our method is going to be is to set it equal to 0 and factor the expression if possible. And that is to say, when we factor, we usually check for a GCF, but we also look for things like differences of squares that we can factor into conjugate pairs, or anything that we would consider to be in some sort of quadratic form, ax squared plus bx plus c form. But if it is factorable, then we're going to set these factors equal to 0 individually. And you'll notice that I wrote here, then complete parts 1 through 3 for type 1 equations. So basically, once we get our factors set equal to 0, we're going to go through this whole process of just isolating it, using an appropriate inverse function, and then determining the angles from the unit circle. So taking a look at these over here, let's first of all talk about why it's not easy to isolate the trig function. So this one here, I have cosine times sine minus cosine. First things first, these aren't like terms. And in terms of getting one of these or the other by themselves, you could, but you'd be getting it by itself in terms of the other ones, so it's not helpful. And so what I would tell you is, first of all, set it equal to 0 and factor it. Recall what I said. I said you look for the GCF first. So I noticed that both of these terms have a cosine of x in common. I'm going to factor that cosine of x out in front, and what I get left with is just the sine x part of this term, since we took the cosine out, minus 1, since I have to put something in this place here to take the place of the cosine we took out in front. The fact is, now that I have it written as this times this equals 0, recall that because of our 0 product property, if 2 or more things multiply out to be 0, then either the first thing was 0 or the second thing is 0. And we could go ahead and say that with 100% confidence. And so the reason why that would be a benefit here is because once you get it factored, we are going to set the factors individually equal to 0, and then we're just going to go solve these separately. So for instance, how would I solve this one here? Well, I'd isolate the trig function like it already is, and then I would just undo it with an inverse trig function and work from there. What are these angles? And likewise here, I could add 1 to both sides, a whole lot easier than I could solve the original equation. Now I've isolated my sine function, so to undo sine, we'll do a sine inverse. From there, I can go look for my angles. The bottom line, though, is, hey, you got to set it equal to 0 and factor it. So that's pretty normal. Let's get used to it. Looking at number 5 here. Now I look at this, and I say, again, I got squared cosines. I've got cosines of the first. I've got a term even that's a constant that has no cosines. And so in terms of GCF, I don't have a GCF. It's really hard to get these trig functions by themselves, but I noticed that this looks a lot like something like this, or at least it looks like it's in quadratic form. So just like we factor something like 2x squared plus 5x plus 3, we're going to factor this much in the same way. Remember that we're undoing this process of foiling two binomials. And so if this factors, it does factor into a couple of binomials. And remember also that we always start with the first two terms. So what terms could I multiply or put up front here in both of these binomials that when I multiply them I get 2 cosine squared? Well, it would have to be a 2 cosine x times a 1 cosine x. So that's really no mystery here. I have to have that. But in terms of what I'm going to put in the rear of these binomials, those things have to multiply out to be positive 3. So maybe what I do is this. I just put like plus 1 plus 3. Thing here is I get my first term and my last term, but what I'm not sure about is this O and I. So we have to check our outer and our inner, and I notice that when I multiply these, I get 6 cosine x on my outer plus 1 cosine x on my inner, and what that gives me is 7 cosine x, which is bad news bears because I need a 5. So we're going to undo this, and we're going to say, well, hold on, what did I do wrong? What I did was my guess, which this is part of the guess and check part, there we go, is that I put the 1 here and the 3 here. Maybe I switch it around and put a 3 and then a 1. And this would still produce a 3 in the back, but when you check your outer this time, you get 2 cosine x, and you check your inner, you get 3 cosine x. Hey, you guys, these add up to be 5 cosine x. So the point of this, right, the point is that I couldn't get them by themselves easily, but now that I have it factored, I can set each of these individually equal to 0, and I can go solve for the trig function, or isolate the trig function. And so setting these equal to 0, in this first case I get cosine of x equals -3/2, which I think it's worth saying when you try to solve this one, that's bigger than 1 or less than -1 in this case, but it's not going to work. This one's going to have no solutions because cosine's never less than -1. But for what it's worth, that's the answers right there, the no solution answer. And then here we could easily set cosine of x equal to 1. Now it's isolated, -1 that is, and we'll do an inverse cosine, and we'll go find our angles. That's your job from there, but the idea was, here's how you get them by itself. So this last example I do want to look at, and especially because what you're going to see is, oh, well, it's kind of hard to get these trig functions by themselves, definitely, and especially because they are different types of trig functions. So what we are going to do is, in this instance, I know that sine squared is related to cosine in this way. Sine squared plus cosine squared of theta is 1. That is our Pythagorean theorem. So what if I just wanted just the sine squared part? Well, what we could do is we could toss the cosine squared over to the other side, or at least subtract it from both sides, and what we get is this statement right here. And so the benefit to knowing this is that I can go here and I can substitute in for my sine squared, I can put in 1 minus cosine squared. And the reason why that's going to be beneficial for us is now everybody's in the same type of trig function. So I'm going to clean up the left side at least a little bit here. I'm going to write it in standard form. That is to say, I'm going to put my thing with the highest exponent first, negative cosine squared. And then I'm going to put negative cosine to the first, and then I'll put my plus 1. And the only other thing that we have to make sure we do here is set it equal to 0. So I'm going to go ahead and do that. I'm going to add 1 to both sides, but we get negative cosine squared theta minus cosine theta, and this would be plus 2. So in this particular case, we're equal to 0. We're going to try to factor this. And as a method of factoring here, I suppose I would want to start by getting a positive leading coefficient in front. So take everybody times a -1, or divide everybody by a -1 if you want to look at it that way. But what we end up with is positive cosine squared theta plus cosine of theta minus 2 equals 0. And so from here we're looking at, hey, maybe it factors. We'll do this unfoiling thing. We'll factor it here. But I suppose I'd have to have a cosine of theta times a cosine of theta to give me a cosine squared of theta. And I would have to multiply, say, a positive 1 and a -2, or -2 and positive 1 here. In this case, because our a value is 1, I know that the things that multiply out to be -2 and add up to be a positive 1 would be a positive 2 and a -1. So I'm going to put plus 2 minus 1. We could even check this here. Check your outer and your inner. We get negative cosine plus a positive 2 cosine is a positive 1 cosine. The idea, you guys, the idea is that we're just factoring to be able to get these factors set equal to 0, so that when I do that, I can isolate the darn trig function. So, name of the game, isolate the trig function. And if you can't do that easily, I want to see you set it equal to 0 and make sure that you can factor it so that we can set factors equal to 0 and isolate trig functions. Cheers.